Let's continue with our review of complex numbers for the upcoming quiz. Okay, so in this one we were asked to find the value of k in each of the following. And here we have 4 minus ki minus 3 plus 2ki equals 1 plus 9i. So the first thing to remember is that the real portion of this and the imaginary portion are completely distinct and independent from each other. So when we combine these two with our subtraction, we're going to end up with 1 for our real portion, which is 4 minus 3. And then for our imaginary portion, we're going to end up with negative ki minus 2ki. And that's going to give us 1 minus 9i. And that has to equal on the other side of the equation, 1 minus ki, excuse me. And that has to equal 1 plus 9i, which means that k has to equal negative 9. Okay. Next one, this multiplication. So let's work it out on the left side and then set the imaginary portion there equal to the imaginary portion on the other side, and the same with the real portion. Okay, so when we multiply, we're going to end up with 3 times 4, or 12, minus 3 times 2i, which is going to be minus 6i, and then minus 12ki, and then plus 6ki squared. Okay, and that's going to end up giving us 12, and then the other real portion will be the 6ki squared, which is going to end up being plus 6k times negative 1, or minus 6k. So that's our real portion, and that's going to be equal to a. Our coefficient for I, we have a negative 6i, and then we have a negative 12ki, and so that, the negative 6 and the negative 12k is going to be equal to our b. So the negative 6 and the negative 12k combined give us our b. And so what we can do is then set up this equation that 12 minus 6k, the real portion on the left side, has to equal 2k, the real portion on the right side, which means that 12 is equal to 8k and k is equal to 1.5. Now, we should get the same value for k when we check the imaginary portion, and when we check there, we get that negative 6i, or just negative 6, the coefficient, minus 12k has to equal negative 16k, and that means that negative 6 is equal to negative 4k, which means that, again, k is equal to 1.5. Okay, moving on to the next one. We just are simplifying here. And so we're going to do our 4 multiplications. We have 3 times 5, which gives us 15. We have negative 3 root 2i times 5 gives us negative 15 root 2. And then again, note the I is not under the square root. And then we have 3 times root 2i, which is giving us 3 root 2i. And then we have negative 3 root 2i times positive root 2i, which is going to give us negative 3 times root 2, which is just 2, times I squared. Okay, when we combine here, we're going to get for our real portion 15, and then here we're going to get negative 6 times I squared, which will give us a positive 6, so we'll end up with a positive 6 here. And then we also end up with a negative 15 root 2i and a positive 3 root 2i, so we're going to end up with a negative 12 root 2i. And so when we combine, we're going to end up with 21 minus 12 root 2i. Okay, next one, we're going to do a little bit of division, which means that we're going to be multiplying by a conjugate. So in order to evaluate this, we're going to multiply by 4 plus 3i over 4 plus 3i. And again, the conjugate will give us the factoring pattern on the bottom of a minus b times a plus b, which means that we'll end up with a squared minus b squared, and we won't have an I term in the denominator, which is what we want. Okay, so in the denominator, we end up with 4 squared minus 9i squared, which is just going to end up giving us 4, or 16, I should say, and then this is going to end up being plus 9, so we're going to end up with a denominator of 25. Meanwhile, we're going to get 7 minus 24i times 4 plus 3i, which is going to give us 28, and then plus 21i, and then minus 96i, and then a minus 72i squared, which ends up giving us a 28 plus 72, or 100, because this becomes a plus 72, and then 21i minus 96i gives us a negative 75i, and again we said that was all over 25, so this ends up being 4 minus 3i, and notice that we divided 7 minus 24i by 4 minus 3i, and our quotient was 4 minus 3i, which means that 4 minus 3i times 4 minus 3i is equal to 7 minus 24i, or in other words, 4 minus 3i squared is equal to 7 minus 24i, which means that 4 minus 3i is a square root of 7 minus 24i. Okay, I to the 7,021. So again, here's our pattern. I to the 0 equals 1, because anything to the 0 equals 1, except for 0 to the 0. I to the first is equal to I squared, by definition, is equal to negative 1. I cubed is equal to negative I. And I to the fourth, we're back to 1. And then I to the fifth, we're back to I, etc. So here we think about the exponents having the value. This is a 4n number, 0. 1 is 4n plus 1 number. 2 is a 4n plus 2 number. 3 is a 4n plus 3 number. And then we're back to a 4n number. And n would be any integer. So when we look at 7,021, 7,021 is a 4n plus 1 number. In this case, n would be whatever 7,020 divided by 4 is. But we know that 4 divides evenly into 7,020, which means that 7,020 would be the same as the 0 here. So I to the 7,020 would be equal to I to the 0, which would be equal to 1. So I to the 7,021 is equal to I to the first is equal to I. And so again, we could do this with any number. If we had I to the 733, well, we would look for the highest multiple of 4 that's less than or equal to 733, which would give us 732, which means that this would be equal to I to the first, would again be equal to just I. And we can do that for any integer value that's represents an exponent for I. Okay, moving right along. Alrighty. Find the equation in standard form for each of the following. The quadratic that has roots of 3 minus I and 3 plus I and a y-intercept of 0, 30. Alright, so we know we're going to have equation of the form a times x minus 3 minus I times x minus 3 plus I. And we also know that so we know this is the general case, y is equal to that. We also know that at 30, when y is 30, we get a times 0 minus 3 minus I times 0 minus 3 plus I. I would recommend that you multiply this thing out here. And let's go through that again, and we'll look at the pattern that emerges. We have x minus 3 minus I, x minus 3 plus I. We get x squared minus 3x minus ix minus 3x plus 9 plus 3I plus ix minus 3i, and then I times negative I is going to be negative I squared, or positive 1. Okay, the negative ix and the positive ix, the 3i and the negative 3i all cancel out. All we're left with then is this square of values, which is just equal to x minus 3 squared, which is equal to x squared minus 6x plus 9. This is the perfect square trinomial. And then in addition, we have this thing here, which is just the I times the negative I, which is a plus 1, which means that our quadratic, with the a back in, is a times x squared minus 6x plus 10. When we substitute, we get 30 equals a times 0 squared minus 6 times 0 plus 10, or 30 equals a times 10, so a is equal to 3. So we end up with a quadratic 3 times x squared minus 6x plus 10, and then fully multiplied out gives us 3x squared minus 18x plus 30. And that is our quadratic in standard form. A couple things to make note of is that whenever we're multiplying an x minus one root and an x minus another root where the two roots are conjugates, we always end up with this piece here as a perfect square trinomial, and then we have to add on the product of whatever we have here and here. In this case, it was a positive number because we subtracted I squared, which meant that we ended up subtracting a negative number. But if we had, for example, root 2 and root 2 here, we would have ended up with by subtracting 2. So this is a pattern. If you recognize it, great, it'll save you time. Otherwise, you can go through this multiplication process and work it out that way. Okay, let's apply that to the next one here. So we want the quadratic that has roots of 5 minus root 2i and 5 plus root 2i. Well, from above, we know that it's going to have the general form a times our perfect square trinomial of x minus 5 squared, and then we also have minus 2 root 2i times positive root 2i, so it means we're going to end up with minus 2i squared, or in other words, plus 2. So here's what we end up with. We end up with a times x squared minus 10x plus 25, and then minus 2i squared gives us plus 2. So we end up with a times x squared minus 10x plus 27. When we substitute in, we're going to get that 4, so we have, this is y is equal to, we're going to get 4 is equal to a times 7 squared minus 10 times 7 plus 27, which means that 4 is equal to a times 49 minus 70 is negative 21, and then plus 27 gives us positive 6, and so that means that we're dividing both sides by 6, so we get a is equal to 2/3, and so that gives us y is equal to 2/3 times x squared minus 10x plus 27, or multiplied out, equals 2/3 x squared minus 20 over 3x plus 27 times 2/3, which is going to be equal to 54 over 3, or 18. Okay. A lot of algebra there. Very doable, though. Okay. Next question. These 2 points have the same absolute value. What is the value of p squared minus q squared? Okay. It's not obvious how knowing that these 2 points have the same absolute value leads us to know anything about p squared minus q squared. So let's do what we do know, which is that the absolute value of p plus 2i is going to be equal to the square root of p squared plus 2 squared, and that has to be equal to the absolute value of 5 plus qi, which gives us 5 squared plus q squared. All right, Can't do much with the square roots on both sides, so we'll square both sides to get p squared plus 4 equals 25 plus q squared. And we're looking for p squared minus q squared, so we subtract q squared from both sides. Minus q squared plus 4 is equal to 25, which gives us that p squared minus q squared is equal to 21. And that's all we were asked for, p squared minus q squared, and that's what we get there. All right, challenge. What is the square root of 13 minus 84i? So we know that a plus bi squared is equal to 13 minus 84i. On the left side, that's going to give us a squared plus 2abi plus b squared I squared is equal to 13 minus 84i. So that means that we can say that a squared minus b squared, because we have b squared times negative 1, which is I squared, that has to be equal to 13. And 2ab has to be equal to negative 84, which is the coefficient of I on this side, and then 2ab is the coefficient on this side. So that means that AB is equal to negative 42, which means that B is equal to negative 42 over A. We rewrite A squared minus B squared to get A squared minus negative 42 over A squared is equal to 13. And we're going to bring the 13 over, and we're going to say A squared. This will end up being minus, so we have negative 42, so we're going to get minus 1764, which is 42 squared, over a squared minus 13 equals 0. We're then going to multiply through by a squared to get that a to the 4th. We'll bring the 13 up to put it in the proper order. Minus 13a squared, and then minus 1764 is equal to 0. Well, this is actually factorable into a squared times a squared, and the two numbers that we're going to be multiplying are 49 and 36. So we're going to have a negative 49 and a positive 36, which means that a squared equals 49, which means that a equals plus or minus 7. And since b is equal to negative 42a, we're going to have 7 minus 6i as one of the options. Negative 7 plus 6i is the other. These are the two square roots. Okay, continuing onward. All right. A plus bi to the third if a equals negative 1/2 and b equals root 3 over 2. Okay. So let's carry this out. We're going to get negative 1/2 plus the square root of 3 over 2. And first we're going to square that. That's going to give us negative 1/2 times negative 1/2 is positive 1/4. And then we're going to have 2 times negative 1/2 times root 3 over 2. So we're going to have plus 2 times negative 1/2 times root 3 over 2. I, that is, 3 over 2i. And then finally we're going to have a plus 3/4, which is root 3 over 2 squared, I squared. So that's going to give us, this will give us a negative 3/4 here. And we have a positive 1/4 and a negative 3/4. So we're going to end up with negative 1/2 for our real portion. And then this is going to end up giving us 2 times negative 1/2, which is negative 1, and so we're going to end up with a minus root 3 over 2i. Okay, very similar, but a little different. Now we're going to take this and multiply it by, basically, its conjugate. Because now, well, exactly its conjugate, because now we're multiplying what we just found, which was negative 1/2 minus root 3 over 2i, times our original negative 1/2 plus root 3 over 2i, because this will give us now our number raised to the third power, and since we're multiplying a conjugate, we know we're going to end up with just a squared minus b squared, or 1/4 minus 3/4 I squared, or 1/4 plus 3/4, which is just equal to 1. In other words, our original value of -1/2 plus √3/2i cubed is equal to 1. And it turns out that another solution, or another cube root of 1, is going to be equal to the conjugate of what we just worked with. So our second cube root is going to be -1/2. And again, up here we started with -1/2 plus √3/2i. So now we could start with -1/2 minus √3/2i. And that would be our, if we raise that to the third power, that would give us 1. So we actually now have 3 cube roots of 1. We have this one, we have our one from the problem above, -1/2 plus √3/2i, and then we have 1. All 3 of these cubed equal 1. And that's all something that's new in a phenomena of the complex plane.